Welcome, ladies and gentlemen, by the presentation of the Pareto Lean Energy Analysis for Identification of Energy Performance Gaps. This work is done by one of my former master students, Kai Korten. He performed two case studies where he applied the Pareto Lean Energy Analysis method. First, let me tell you something about my background. I'm a full professor of building services at the Faculty of the Built Environment of the unit Building Physics and Systems of the Technical University of Eindhoven. I'm working there since 2001, and besides being a full professor, I also work 1 day a week at an installers company for which I already worked 36 years. When we look at the goals of the Paris Agreement, where we have to reach nearly energy neutral built environment by 2050, we see that in reality building energy efficiency is only slowly increasing. This is due to the low renovation and replacement rates, as well as caused by the energy performance gap. One of the causes of the energy performance gap are the brief phase, the design phase, the construction phase, and the use phase. And especially where we look at the construction phase and the use phase, these are very critical due to pure commissioning. And that really means that during the use phase, which lasts most of the time 20 to 30 years, the building will use much more energy than intended by the design. If we look at the context of the Netherlands, we really have a huge problem. From studies, it follows that around 70% of the buildings, their HVAC systems are underperforming. And that has a huge effect. The energy consumption is 25% higher than expected. Just imagine. So if you look at the whole energy consumption for the building sector, then it is around 36% of the total energy consumption. Of this, then, 9% is wasted. And that is 5 times the current wind and solar generation which has been installed in the Netherlands. So this benefit of increasing the performance of the HVAC systems is huge. It's 5 times the energy which is now currently being generated by wind and solar in the Netherlands. How can we do it? Well, one of the measures that you could take is continuous commissioning. And one of the prerequisites for continuous commissioning is that you have data of the performance of the building management system and that you apply data mining techniques. Data mining techniques consist basically out 5 steps. So the selection of the data from the building management system about the performance of the building's installations. Then you have to define the target data. Then in step 2, you have to pre-process this target data. Then in step 3, you have to transform that data so that you can apply data mining to find certain patterns in the data, which you can interpret it, and by this interpretation, the original data from the building management system becomes information and knowledge which you can use to improve the control strategies of the building. As this is quite a lot of work, if you just imagine when you have just a normal office building which has 1500 data points giving data every 3 minutes, and when you have collected the data for 4 or 5 years, you're talking about an enormous amount of data. So one of the reasons behind our research is that we were looking for effective strategies which could be used to improve underperforming heating and ventilation air conditioning systems using data mining techniques. Because if you look at the data mining, then this first step, the selection of the data and the pre-processing of the target data, is really 80% of the work and value which is involved. So basically you dig into a whole pile of data and you really want to find the needle in the haystack. You only want to find the most important information, but you really have to go through all the data. So therefore, we applied and developed a methodology, and that methodology consists of different steps. And the first step is an application of the Pareto analysis, where we look for the most influencing parameters. The reason and underlying logic behind the Pareto analysis is that from practice we know that 80% of the problems can be identified by 20% of the causes. So that really means if you look at the graph, that instead of looking at, for instance, all the 10 different parameters, you can only look at the first two. And by looking at the first two, we only have already identified 80% of the problems. So that's first a very important step to be much more effective in the data mining and data analytics. When we look at the steps of the Pareto analysis, then first step is the identification of the problem, then followed by the identification of the causes of the problem, then rank, score, and group of the causes, and then the fourth step is the assessment of the energy gap by the critical parameters. Here you see complete basic steps of the Pareto analysis that were applied. So identification of the problem, identification of the root causes of each problem, rank and score the problems, group problems together by root cause, add up scores for each group, and then take action. This first step is then followed by a second step where we look at the performance analysis, especially for the system inefficiencies. And the steps of the performance analysis are analyzing design performance, collect data, analyze measured performance, and determine the system inefficiencies. That second step is then followed by a third step, which is the lean energy analysis. And this is performed to really get to an improved performance of the systems and inefficiencies that were decided and determined in the second step. When we look at the steps, individual steps of phase 3, then step 1 is collecting data of the system inefficiencies. Then in the second step, to create a baseline and reference regression model. Then the third step, create a benchmark framework with regression coefficients of the reference models. And step 4, assess the energy efficiency by regression coefficients. This methodology was applied on different case studies, and here we only show you the case study of a care center which was constructed in 2016 and which had a gross floor area of around 7,000 square meters. Here you can see the data that is being collected and the principle, flowchart principle of the care center. So we have gas, we have two gas boilers, and we have a central heat pump which is connected to a aquifer thermal energy storage system. And we have 3 different air handling units with heat recovery. We have radiators, we have some duct heating overall. So this is really energy efficient design and also state of the art. Especially interesting is aquifer thermal energy storage system, which allows you to store cooling in the winter and use it for the heating and use it for cooling in summer, and also by using the cooling in summer, store the heat, and then can use the heat for the heating in the winter. And so we have a cold and warm well. It's connected by a heat exchanger to the installations of the building, and then it can be interacting directly with the heat pump, or it can also directly interact with the heating or cooling coil of the air handling unit. And it allows you to store the energy, and by using small temperature differences, it increases the coefficient of performance of your heat pump system. So this is quite a very popular approach in the Netherlands, because our soil is very good suited for application of these aquifer thermal energy storage systems. So when we now look at the first step of our approach, which is basically the step number one of the Pareto analysis, then we really want to identification of the problem. So what we here see is an overview of the annual primary energy consumption of the care center. And you can see that, yeah, the design value is absolutely not met. The real measured energy consumption is much higher. Also, you can see that in principle, of course, it was quite an energy efficient design. So if you could compare it with the average, then it's almost 30% below the average energy consumption of a care center in the Netherlands. But in this case, you can see, it's more than 25% energy more than intended. So in the second step, we looked at the different possible causes of this problem, and we ranked and scored them and grouped them. So here you can see the different parameters that we looked at for heating and for cooling. So you can see, for instance, the maximum heating supply, heat recovery, set points. So we looked at all the different parameters and their influence. And as you can see clearly, you can see here immediately that the first two have the major impact on the effect of the energy consumption. In the third step of the Pareto analysis, which is basically step 6, we looked at the assessment of the energy gap by the selected critical parameters. So we looked at the heating and cooling, and we especially looked at, so here we can see the energy demand in relation to the outside temperature. And you can see that there is quite a spread in the energy demand, which really means that you that this dotted line could be the optimum. So you can see easily that there's a huge variation, and which means that you will use more energy in those moments. So that's why we looked from the system perspective and applied the LEO energy analysis, the energy analysis. Step 2, where we create a baseline benchmark of the model. So here you can see the daily outside temperature versus the daily mean heat extraction. So we really looked at how much energy can we extract from aquifer thermal energy storage. And here you can see the models that were being generated for heating extraction as well as for the cooling extraction. So that gives us a benchmark model to compare with the real energy consumption with. So in the fifth step, which is then step 3 of the lean energy analysis, and we really identified energy gaps with rejection coefficients of benchmark regression models. So on the left side, you see the predicted heat extraction, and you see the measured heat extraction, and in the middle you see the residential, so the difference between them, and here you can see in this histogram relative frequency of the residential residuals, and so the difference between the measurements and the prediction. Here in the graph, we have represented the historical measured data and the predicted data. And here you can see that so you can see the red line is the measured heat extraction from the aquifer thermal energy storage system, and in the blue line the predicted. So immediately you can see during which circumstances and which data sets the biggest differences occur. And that, of course, is our main point of interest to see, hey, what can we do during those moments to improve our control. Here you can see the same for the cold extraction. And you can see here, for instance, if you look at during June 2018, there's a huge difference as well as in the beginning of July 2018. So these differences are much bigger than the difference that occurred by the heat extraction. So here, when we look at the indication of the yearly energy saving potentials, then we see that for the heat extraction, the energy saving potential is around 3 kilowatt hours per square meter, so which is representing an potential energy saving of 7%. But the major important factor is the cold extraction, where we discovered that you can have an energy saving potential of not less of 16 kilowatt hours per square meters. So that will has a potential energy saving of 70%. So to conclude, our research question was we are looking for an effective strategy to improve underperforming HVAC system using data mining techniques. The first step was to investigate efficient models to reduce the necessary data for effective data mining techniques. And the second step was the use of the combined Pareto lean method, which had a clear added value in the case studies. And using the strength of both resulted in a successful and effective and efficient combined method. I'd like to thank you for your attention, and when you have questions, you can mail me w.zeiler@tue.nl. And yeah, as you can see, it's really very important to be more effective in selecting the needle from the haystack that you're really looking for. Just applying data mining will end up in an enormous amount of work and also an enormous amount of additional problems. So it's really very important to focus on what you really want to get out of it. And that, of course, is those situations where you can really, to a large extent, improve the energy efficiency of your heating and ventilation and air conditioning systems. Again, thank you for your attention.